All right, so what we're going to be talking about today, if I can get the right window open, is resistor combination techniques. So I am incredibly hopeful that this is all largely review. So really, you're just going to learn why you were able to do things that you've been doing for some point in time at this point. All right, so let's see. So we're going to start by talking about resistors that are connected to each other in series. So I'm going to draw a simple resistive network, and I'm going to use these ellipses to indicate that we are thinking about this in the context of a larger network if necessary. Let's say that I have some resistor R1 like so, a resistor R2 like so, all the way out to some resistor R sub n. So let's make an assumption here. It doesn't necessarily have to be true, but it'll do a little bit better job of explaining what's going on. So let's assume that this network is energized, meaning that there is some total voltage drop across all of these resistors that are connected in series that I'm going to call V. And since there's some total voltage drop across all of these resistors, I should observe some current flowing through all of these resistors connected in series. And I'm going to call that current I. Okay. So what I'm going to do now is I am going to assign individual voltage drops across each of these resistors, and I'm going to choose to put the positive polarity terminal on the side so that the current I is going to flow into the positive polarity terminal and out of the negative polarity terminal. And I'm doing that just to make sure that when I perform Kirchhoff's voltage law here in a moment, all of my resistor voltage drops are going to have a plus sign, okay? So I might call this voltage right here V1. The voltage drop across resistor R2 would be V2, and the voltage drop across resistor Rn would be Vn, like so. So if I were to apply Kirchhoff's voltage law, what I'll see is that I'll have negative V, my total voltage, plus V1 plus V2, all the way out to some V sub n is equal to 0. And so the first thing that I'm going to do here is a very simple thing. I'm just going to move that V to the other side of the equal sign. So I'm going to say essentially that total voltage drop must be equal to the sum of all of the individual resistor voltage drops. So that would be written in something like this. V is equal to V1 plus V2 all the way out to V sub n. Now what I can do is I can express all of those resistor voltage drops in terms of that common current I that's flowing through that series network. So just using Ohm's law, this is going to look like R1 times I plus R2 times I all the way out to R sub n times I. And I can very easily see that there is a common factor of I, the current flowing through everything. And so I can factor that out. And so that's going to look like I times R1 plus R2 all the way out to R sub n, like so. Now, at the beginning of yesterday's class, we learned that resistance is the constant of proportionality seen between voltage and current. So we could say that the equivalent resistance of this network, REQ, is just going to be the ratio of the voltage drop across the terminals of the network divided by the current that's flowing into the network. And that will give me the result R1 plus R2 all the way out to R sub n, or put more succinctly, using a summation notation, we could say that the equivalent resistance is simply the sum from I is equal to 1 to n of R sub I. So whenever we have resistors in series, we can simply just add them all up directly. You guys probably already knew this, but now we've formally proven it using Kirchhoff's voltage law and Ohm's law. Okay. So before we move on to resistors in parallel, any questions about this guy? All right. So now let's look at parallel combinations of resistors. So I'm going to draw a similar network, but instead of having all of my resistors connected in series, I'm obviously now going to have them all connected in parallel. So it would look something like this. So here's some resistor R1, some resistor R2, all the way out to some resistor R sub n. So what we're doing here will work for any number of resistors connected in parallel. And once again, I'm going to assume that my system is energized so that there will be some voltage drop V across the terminals of my network. And there will be some current I flowing into the terminals of my network. And in this case, I'm going to choose to express all of my resistor currents. Excuse me. I'm going to label them. I'm going to choose to put them all flowing down. And the reason why I'm choosing to have them all flow down is because that means the currents would be flowing into the positive polarity terminal of that common voltage V. And once again, all of my Ohm's law relationships will just have a plus sign. So I'm doing this to make sure I don't have minus signs all over the place that are unnecessary. So let's call this current right here I1, this current right here I2, and this current right here I sub n. So if I were to apply Kirchhoff's current law to this network, so let's say applying KCL number 1 at our top node. So KCL number 1 is currents flowing in equal to currents flowing out. The only current that I have flowing in is my current I. And the currents that are flowing out are each of those resistor currents, I1, I2, all the way out to I sub n. Once again, I can use Ohm's law to express all of those resistor currents in terms of that common voltage. So that's going to look like I is equal to V over R1 plus V over R2 all the way out to V over R sub n. And since I have a common factor of V, I can factor that guy out, and that's going to leave me with I is equal to V multiplied by 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. Once again, we can find the equivalent resistance for this network as simply the ratio of the voltage drop across the terminals of the network divided by the current flowing into the network. And so this is actually going to give us 1 over R1 plus 1 over R2 all the way out to 1 over R sub n, or in summation notation, this might look like 1 over the sum from I is equal to 1 to n of 1 over R sub I. All right, so we're going to talk a little bit more about the equivalent resistance of parallel elements here. Essentially, there is a special case that we can use a much simplified version of this 1 over the sum of the reciprocals formation. So whenever I have, let me just scroll down here. Whenever we have exactly 2 elements connected in parallel, so that would be a situation like this, where I've got some resistance R1 in parallel with R2. We could say that our equivalent resistance is going to be 1 over R1 plus 1 over R2 using the relationship that I just showed you guys a moment ago. Now, what I can do to this guy is I can actually multiply that factor of 1 over R1 by R2 over R2, right? That's perfectly acceptable because that's just a fancy representation of the number 1. And pretty similarly, I can multiply 1 over R2 by R1 over R1. And so what that has done is it has effectively given me a common denominator in my denominator of my overall fraction. And so I could rewrite this as 1 divided by R1 plus R2 divided by R1 times R2. And since I have 1 over that fraction, I can simply take the reciprocal of this guy, and it will give me the relationship R1 times R2 over R1 plus R2. So that is the shorthand method for calculating the equivalent resistance of exactly 2 resistors connected in series. It does not work for any more than 2 resistors. So you're going to see me do this a whole heck of a lot instead of the 1 over R1 plus 1 over R2, because it's easier to put in my calculator and all of that kind of good stuff. So just in case you weren't introduced to this method back in your Engineering 120 series, you have now been introduced to it, and I suggest that you get familiar with it. Okay, so before we move on from here, are there literally any questions? Do not be embarrassed. The whole point of this class and me being here is for you to ask questions of me if something doesn't make sense. So any questions whatsoever? All right. So unfortunately, we are not always going to have networks where everything is connected in series or everything is connected in parallel. We might have a more complicated network, maybe something like this. So this is literally one of your web work problems. This is homework 3, problem 2. And I am going to work one of these parts with you to illustrate how we can figure out the equivalent resistance when we have a more complicated network and it's not intuitively obvious how everything is connected, okay? So for a network like this, I typically start by identifying all of my different nodes, and I'll do that using different colors like we did on the first day of class. So I'm going to have a red node up here in the top left-hand corner. Let's say we have a blue node here in the top middle, a green node here over on the top right, a light purple node here in the bottom left, a pink node here in the bottom middle, and an orange node here on the bottom right. So before we go anywhere beyond this, have I correctly identified all of my nodes? Yeah, okay. So luckily enough for us, 4 of them have already been labeled with terminals A, B, C, and D. So what I'm going to do now is I'm just going to give each of the 2 nodes that don't have a pre-existing label a new label. Because I am boring, I'm going to choose simply E and F. Okay. So our ultimate goal here is to find the equivalent resistance between some specific terminal pairs that were defined in the problem statement on WebWork. So we could find it between terminals A and B, between terminals B and C, or between terminals B and D. So which of these 3 terminal pairs do you want me to find the equivalent resistance? A, B, or C? B. Okay. So we're going to find the equivalent resistance seen between terminals B and C. So how I like to do this, I'm a child of the 80s. I grew up watching TV shows like Pee-wee's Playhouse and stuff like that. And so I like to do resistor combination by playing connect the dots, essentially. Okay. So what I'm going to do is I'm going to put terminal B over here on the left-hand side of my page, and I'm going to put terminal D over here on the right-hand side of my page. And then I'm just going to figure out how everything is connected between these 2 extremes, okay? And I'm going to make sure that every resistor is used exactly once, okay? So if we're finding the equivalent resistance between B and D, what's the easiest way for us to go from node B to node D? Straight down through that 50 ohm resistor, okay? So I'm always going to start with the easiest possible path first, which is just that 50 ohm resistor. So here's the 50 ohm resistor in the middle of my page, okay? And I'm going to put a little check mark by this guy to remind me that I've used it in my equivalent resistor network. So what are some other ways that I can go from B to D? So I could go from B to C to D, all right? So I'm going to put C in the middle of my page. How do I go from B to C? Through that resistor R2, and we're told up at the top that R2 is equal to 160 ohms. So I'm just going to put a resistor having a value of 160 ohms between B and C. I'm going to put a check mark by this guy. Now, how can I go from C to D? So through R4 is one way, where R4 has a value of 20 ohms. Is there a different way that I can go from C to D? From C to E to D, absolutely right. So halfway between C and D, I'm going to put node E. How do I go from C to E? Through the 100 ohm resistor. And then I go from E to D through the 25 ohm resistor. All right. So it seems like I have the left-hand half of the circuit pretty well taken care of. So now let's focus on the right-hand half of the circuit. So how do I go from B to D using the right-hand half of the circuit? So I could go from B to A. So I'm going to put A down here. From B to A is the resistor R1, which has a value of 80 ohms. How can I go from A to D? So through R3 is a direct path, and R3 has a value of 160. Are there any other ways I can go from A to D? Through F. So going from A to F would be, let's see, through the 75 ohm resistor. And finally, from F to D would be through the 200 ohm resistor. So I now have this kind of ladder-like structure. I believe I've taken into account all of my resistors. Let me put check marks by these guys. R3 was that 160. Yeah, there we go. And so what I would tend to do here is I would literally just start from the bottom, simplifying things and working my way towards the top, right? So what's the first simplification that I could make? 75 is in series with 200. So effectively, I'm going to have a new resistance between A and D that is 275 ohms. All right. What's the next simplification that I could make just working my way from the bottom to the top? So 275 and 160 are in parallel. All right, I can't do that in my head, so let me throw it in a calculator. So 275 times 160 over 275 plus 160 gives me 8,800 over 87. So because both of these resistors are between nodes A and D, the equivalent resistor that I'm replacing them with needs to be between A and D as well. So 8,800 over 87. All right. Now what simplification can I make? So 80 and 8,800 over 87 are in series. So let me just do plus 80. And that gives me 15,760 over 87. So that's going to be between B and D. And essentially, I have now found the equivalent resistance of everything to the right of that 50 ohm resistor that was in the middle of my circuit. I can't make any more simplifications to that particular path because it's down to a single resistor. So I need to move up to the next rung in my ladder. So what's the next simplification that I can make? 100 is in series with 25. So that's going to look like 125. What comes next? So 20 and 125 are in parallel with each other. So 20 times 125 over 20 plus 125 gives me 500 over 29. what can I do from here? So 160 and 500 over 29 are in series. So I'm just going to add those two guys together. So just plus 160. And I get 5140 over 29. And now I've reduced this network down to effectively just 3 resistors in parallel. So RBD is going to be the parallel combination of 50 ohms in parallel with 5140 over 29 ohms in parallel with 15760 over 87 ohms. That's just a shorthand notation for saying that two elements are in parallel if you put two vertical lines between them. Mathematically, I would evaluate this as 1 over 50 ohms plus 29 over 5140 ohms, right? So that's just the reciprocal of that middle resistor, plus 87 over 15760 ohms. And when I put this into my calculator, I got 32.0900. So let's just call it 32.090 ohms. Carter. What do you mean? What if you short out the 50 ohm? The resistance would be 0. So actually, let's look at the in-class assignment because that will have a short circuit, and we'll talk about how we'll handle that. But before we do that, does anybody have any questions about what we did here? I'm sorry, what? You got 50? Then you are very wrong. So there's no way in hell it could ever be just 50. So let me explain why. Yes. So there is 50 ohms of resistance directly between B and D. Then there's some equivalent resistance to the right. And there's some equivalent resistance to the left. And those equivalent resistances are parallel with that 50. Anytime we have resistances in parallel, it will the equivalent resistance will always be smaller than the smallest resistance. In this case, so let's see, 5140 over 29 is 177.24 ohms. 15760 over 87 is 181.15 ohms. So our answer is definitely going to be less than 50 if 50 is the smallest resistor in that parallel network. Okay. All right. Any other questions about this guy before we move on? Okay, so we're going to work in-class assignment problem 1 together, and then I'm going to leave problem 2 for you guys to do if you happen to finish up the lab a little bit early, which is always a possibility because this lab's pretty easy. All right, so we have this network, got 4 terminals, A, B, C, and D, and we are asked to determine the equivalent resistance seen between terminals A and B. So this process is going to be pretty darn similar to what we just did, okay? So the first thing that I'm going to do anytime I see a network like this where I don't really, I can't intuitively see exactly what's going on, I'm going to start by identifying my nodes. So here is one node. Then I'm going to have this node up here, this node over here, this node here, this guy here, this guy here, and lastly, this guy here. Much like the last example problem that we worked, if one of our nodes doesn't have a label, I'm just going to choose to give it one. So A, B, C, and D are already taken. So I'm going to start, this guy is going to be E. This guy will be F. This guy will be G. And this guy will be H. So before we get into rewriting this guy, what does it mean that terminal A and terminal C are both touching the red node? They're the same thing. So A and C are effectively interchangeable. Okay. So we're not going to actually use the letter C at all here, because if they're both touching the same set of wires unbroken by any resistances, they're both touching the same node point. So there's really no need for me to have them labeled as two different nodes, because they are literally the exact same node. Okay. So we'll talk about that in just a moment, but the short answer is kind of yes. Okay. So assuming I'm thinking about the same resistors that you're thinking about. Okay. So let's talk about what happens when we have something in parallel with a short circuit. Yes, sir. So if there is an element, any element in between that's breaking up those nodes, they are not the same node. Yeah. Okay. All right. So whenever I have the same color or the same node touching both terminals of a resistor or an equivalent resistance, I can say that that resistor or that equivalent resistance is shorted out, okay? So I want to explain what that means mathematically real quick, okay? So we learned a couple of moments ago that whenever I have two elements in parallel, REQ is just R1 times R2 over R1 plus R2, right? We used that a couple of minutes ago. What's the resistance of a short circuit? 0 ohms. So if we replace resistor R1 with 0, what is the result of this parallel equivalent resistance going to be? 0 ohms. So essentially, anytime I have a resistor that is shorted out or is in parallel with a short circuit, I can just throw that resistor away without losing any information whatsoever, because I know that it's not going to contribute to the equivalent resistance at all. So which resistors in this network, if any, are shorted out? So the 6 ohm resistor is definitely shorted out because it's touching the red node on both sides, okay? Now, the 25 ohm resistor and the 23 ohm resistor are connected in series, and the equivalent resistance of those, which would be 48 ohms, would then be touching the red node on both sides. So I can effectively just short out this branch as well. So anything that's in parallel with a short circuit, I can throw away without losing any information. So I've made a pretty significant simplification here Now I'm at a point where I can start drawing my equivalent circuit. So anybody have any questions about concept of shorting out resistors? All right. So if I'm trying to find the equivalent resistance between A and B, much like I did in the last example, I'm going to put A on the left-hand side of my page and B on the right-hand side of my page. So what's the most direct path from A to B? Down through the 9 ohm resistor. Okay. So that guy's taken care of. So what's the next simple path to go from A to B? So A to G to H to D to B is the next simple path. It has a lot of intermediate steps, but so I'm going to put G right here. From A to G is the 15 ohm resistor. From G to H is the 12 ohm resistor. So let's put H right here. From H to D is the 11 ohm resistor. So we'll put D right here. And lastly, from D to B is the 16 ohm resistor. Like so. So we took care of this guy and this guy and this guy. So what's left? The 20 and the 8. So the 20 is connected to A, and the other side of the 8 is connected to G. So between A and G, I now have this alternative path. So from A to E, excuse me, that should be F. My apologies. I'll have the 20 ohm resistor. Maybe should have given myself a little bit more room here, but that'll be okay. And then from F to G, I have the 8 ohm resistor. So how would we simplify this guy? So 20 and 8, so that's just 28. What's next? In parallel with the 15, so that's 28 times 15 over 28 plus 15. What's next? So that's 420 over 43. So in series with the 12 and the 11 and the 16. So that's going to look like 2097 over 43. And then lastly, I just have two resistors in parallel. So that answer times 9 over answer plus 9 gives me an equivalent resistance of 699. So let me just write this here. 699 over 92 ohms, which is 7.5978. So let's call it 7.598 ohms. And I'll be damned if that isn't the answer that I provide. So like I said, I'm going to leave problem 2 for this end class assignment, which is just finding the equivalent resistance between C and D for you all to do if you have time after you wrap up your mini lab. So if anybody has any questions, I am more than happy to answer them. If not, you can go ahead and get started on your mini lab. They do not require any external pieces of equipment. So if you've got a breadboard and actually, if you just have your kit and your mini lab sheet, you can actually just do this at your table. Let me find some wires for you for the later part.